All right, section 2.8, the derivative as a function. So this is going to continue our discussion that we were having in section 2.7 about, with that limit definition of the derivative. So, remember I told you these two sections were very similar to each other, at least in some of the things that it talks about, and it's mainly with respect to this limit definition. But there's other things that we're going to address in this section as well. All right, so in section 2.7, we talked about the derivative of a function f at a fixed number a. Right, that's what we looked at in the previous section. So we had this definition for the derivative. We said f prime at a is equal to that limit as h approaches 0 of f of a plus h minus f of a over h. All we're going to do now is take the next step and say, okay, well, let's broaden that to just talk about the entire function. So instead of just focusing on a single point, an a value, it's the same idea. If we let the a value vary, right, and we let that be any x value in the domain of our function, we'll talk about more about that as we go through, then we can broaden our definition and say, okay, now let's talk about the derivative of the function. All right, so f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This is our derivative of the function f. So this is our broadest definition. So again, it's kind of splitting hairs. Do I use f prime of a? Do I use f prime of x? Use f prime of whatever your independent variable happens to be. So in generic form, it's f prime of x. So don't get too hung up on that. That's it's notation, right? But it's all with respect to the variable that you're using. But geometrically, as we said, when we talk about the derivative representing the slope of the tan line, so here f prime of x is the slope of the tangent line to the graph of our function f at the point x f of x. But again, now we can choose any point on the graph and define the derivative there. But it's the slope of the tan line. We said it's the rate of change in the function, or how the graph is changing at that point. Now, notice the notation. We didn't talk, now that we're kind of putting this in the context of a function, right? So f of x is a function. It has a domain. Well, the derivative, f prime of x, is also a function. So it has a domain. We're always interested in the domain of our functions when we're working with them. Now, this is a real fancy definition. The domain of f prime of x is all values of x such that f prime of x exists. Well, that doesn't tell me a whole lot. I can say that for the function as well. So anywhere where there is a derivative, or the derivative exists, is in the domain of our function f prime of x. Now, that domain may be the same as our function, or as the domain of our function, or it could be smaller than the domain of our function. What it can't be is larger than the domain of our function. In other words, whatever the domain of our function f is. All right, so those are all the values of x, that there are points on the graph corresponding to those x values. I can't find the derivative of a function at a point that's not on my graph. So in other words, for an x value that's not in the domain of my function, there's no point on the graph, there's no derivative there. Okay? There's no tan line that could touch the graph at that point because there is no point. So what that means essentially then is the domain of our function and the domain of our derivative could be the same if I could find the derivative at every single point on the graph of my function. But there could be points on the graph of my function where I cannot find the derivative. And so we're going to talk about that as we go through this section. All right. So the domains could be the same. The derivative could have a smaller domain. Definitely the derivative cannot have a larger domain than the original function. Here's an example, so we're going to do some more examples with that limit definition in this section. There's nothing different here other than instead of using f prime of a, we're using f prime of x. But it's exactly the same process, so same definition. But what I do want to talk a little bit more about is exactly what this tells me about the graph of our function. So let's let f of x be our basic little quadratic function. F of x equals x squared. Then the derivative, f prime of x, right, that's our limit as h approaches 0, f of x plus h minus f of x all over h. So what is f of x plus h? Plug x plus h into our function. So I get x plus h squared minus f of x, which is x squared, all over h. And then we play the game from there. Like I said, as soon as you plug everything into that limit definition, now it's all about evaluating the limit. And so that reverts back to everything we talked about previously. So I'm going to simplify. We square the binomial x plus h squared minus x squared Combine a couple of like terms. I've got 2xh plus h squared all over h. And then notice again here we could factor out that common factor of h, which will divide out with our denominator. And I'm left with 2x minus h, limit as h approaches 0. And again, that limit definition comes with me all the way through this step by step until we are actually able to plug 0 into our function. And now I've got 2x minus 0, or simply 2x. So for the function f of x equals x squared, f prime of x is the function 2x. Now I want to look at the graphs of these two functions. I mean, these are two basic little functions, right? F of x is our basic quadratic, it's a parabola. F prime is simply a linear function, right, a line with a slope of 2. So these are basically what the two graphs look like. Now what I want you to recognize is what that, or why the graph of the derivative looks the way that it does. And what I would ultimately be interested in here is, could you look at the graph of the derivative and have an idea about what the graph of the function looks like, okay? I mean, because I can remember what the derivative tells me. The derivative tells me the slope of the tangent line to the curve at the point, or basically it's the slope of the curve. I mean, I can look at the curve and tell you what the slope is. But what I'm interested in going forward is, if I know what the derivative is, what does that derivative tell me about the function? That's going to be the useful point. So what I want you to notice here, notice on the graph of our function, I find sometimes students just kind of, I guess it's just the visual, the fact that you're looking at two graphs. Remember what these represent in conjunction to each other, especially what the derivative means with respect to the original function. So remember, we're talking about the slope, right? So if I look at this left side of the parabola, right, where the slope is negative, m is 0 here. So notice then when I look at the graph of our derivative, the function values, right, up to the point where I hit 0 are negative. Now not only that, notice as we move along this curve, the slope is getting smaller. Right? I mean, it's negative, but it's getting less and less negative as I travel along the graph. So notice again, when I go over here to the derivative, these are negative values, but they're getting smaller and smaller negative. Right? The values of the function itself are approaching 0. When you hit this point at the origin for this particular function, there's a horizontal tan line. And we talked about those horizontal tan lines in the previous section. We know the slope there is 0, so notice at that point on the graph of our derivative, we're at the origin, and the value of the function there is 0. Right? It passes through the origin again, but that's just simply because we're at the point where x equals 0. The value of the derivative is 0. And then the right side of the parabola, right, we have positive slope as we move along this side. So notice the function values here are positive. And the graph is getting steeper, so the values of the derivative are getting larger. Right? So, you know, the idea is, can I look at this? And if I gave you a graph like that, could you sketch the graph of the function? You know, at least reasonably so. I mean, it's all about just having a general idea of what the graph looks like. Doesn't have to be perfect. Now, this next example, I'm going to talk about this one. I'm not going to hold you to something like this for a test, but I'm just going to ask you to look at this. There's a couple like this in your homework, just to see if you can make some observations. What they're asking you to do is to look at the graph of a function and estimate the value of the derivative for each of those given x values. Right? Now what does that mean? Well, remember, when I'm looking at the graph, what does the derivative tell me? The derivative tells me what the slope of the tan line is at that point, or what the slope of the curve is at that point. So when we say, for example, for part A, it says find, or what is f prime of 0, what I'm looking at is what is the slope of the tan line to the curve at that point. Now that's not an easy thing to give an exact value for. I mean, you should be able to make some decent observations. If I draw a line tangent to this thing, see if I could draw one halfway decent here. If I can actually hit the curve, right? But you're looking at drawing a tan line that hits the curve at exactly that point in the direction of the curve, and then you want to tell me what's the slope of that line, right? Because that's what the derivative is. Right? Again, that's not an easy thing to do just by looking at the graph. I mean, you could draw the line. If you draw it perfect, you can look at the blocks and maybe do rise over run and that kind of thing. I'm not interested in that. I'm interested in you just having that general idea. Notice here it says f prime of 0 is 6, so the line that I just drew would have a slope of 6. Now f prime at 1, that you should be able to tell me, because notice where x equals 1, our tan line would be horizontal. Right? That's of particular interest. We are absolutely interested in these going forward, especially when it comes to application problems, where that derivative is equal to 0, where you have those horizontal tan lines. Those guys are very, very useful as far as giving me information about my function. Right? But notice they're kind of easy to tell by looking at the graph. It's where you have those turning points, that kind of thing. So what I don't want to get into is, you notice, like, look at f prime of 3. F prime of 3, they're telling us is negative 1.3. Would I expect you to look at this graph and say that at x equals 3, if I drew the tan line at that point, right, kind of something like that you could tell me that the slope of that line is negative 1.3? Absolutely not. Now, you can tell me the slope of the tan line there is negative, because that's what we talked about with that previous example. So I'm at least interested in the fact that the slope here is positive, the slope here is 0, the slope here is negative, the slope here again at 6. So you should be able to tell me that f prime of 6 is 0, because that's the slope of the tan line. And then the slope gets positive again. So it's that kind of observation that we're interested in. Where is the slope 0? Where is it positive? Where is it negative? But being able to give the exact value, no. Reasonably so, yeah, sure. But so to look at a couple of those in the homework, but don't worry too much if you say, okay, it looks like it's about -2, and you look at the solution, it tells you it's negative 1.6. Don't cry over that. That's fine. Okay. So just play with that a little bit, see if you can make some observations. But that's really what I'm interested in there. So then the next example, and again, just a couple more with the derivatives. I want to get the graphs. So I've got f of x equals x cubed minus x, right, as our next function. So we're going to find f prime. And again, this is using the limit definition of the derivative. So same when I talked in that previous section. If you're asked to use a limit definition, then you're using this definition. Or again, you could use that limit as x approaches a of f of x minus f of a over x minus a, if you prefer. But that's our definition. Limit as h approaches 0, f of x plus h. So I plugged in x plus h, which gives me x plus h cubed minus x plus h minus f of x all over h. And then from here we're simplifying. Now that's x plus h cubed, so you would have to multiply that thing out. X plus h times x plus h times x plus h. And you end up with this. And then minus f of x, so I went ahead and distributed the negative all over h. And then we're combining some like terms. Notice again, all of those terms have an h, that if you factor out that h and divide it out with the h in the denominator, you are left with this. And again, that limit statement goes every step of the way until the very end. I can now actually plug in h equal to 0. So that would make this 0, that would make this 0, and I'm left with 3x squared minus 1. So there is f prime of x. All right, so again, that's all just basic algebra. And once you plug everything in, it's simplification. It's basic algebra from there. I trust you can simplify those expressions. And then look at the graphs of these two functions. Right? So like we did with that previous example, the first graph, the one on the left, that's the basic shape of the graph of x cubed minus x, our original function. And then I've got the graph of f prime, which is 3x squared minus 1 on the right, which is a basic parabola, right? It's a quadratic. So notice again that same kind of observation that we had in that previous example. If you look at this part of the graph, right, the slope is positive. So when I go over to the graph of f prime, I've got positive values for the slope here. Now remember, don't look at the slope of this. I think that's what confuses people. We're not looking at the slope of that curve. What I'm doing is I'm using the function values here to describe the slope over here. That's what you're describing. So the fact that the slope is positive on that function on f of x means that I have positive function values on the graph of f prime. And also notice again, as we move along the curve here, the graph is getting less steep. The slope is decreasing. So notice over on the f prime, the slope values are getting smaller. And then once we hit this point, there's our point where we have a horizontal tangent. So notice on the graph of our derivative, that's where our slope is 0. The value of the function f prime at that point would be 0. That's really a good observation because that tells me where I have an x-intercept. All right, so when we talk about those horizontal tangents on the graph of our function, graphically, that's going to give me the location of x-intercepts on the graph of f prime. You know, we're always interested in x-intercepts. Then we hit the next piece of the graph. Here our slope is negative, right? So on the graph of f prime, we have negative function values between those two points. Now, notice too, right, that it kind of starts off here, it gets steeper, and then it starts getting less steep. So notice the value of our derivative gets bigger negative, it's getting steeper, and then it gets less steep. So the slope values get smaller, negative. Then we hit that next point where we have another horizontal tangent. So that's where we have another x-intercept on the graph of our derivative. And then we have positive slope from that point forward. So our slope values here now are above the x-axis. They're positive. Okay? So yeah, it's being able to look, and like I said with the previous example, it's being able to look at the graph of this. Here's our derivative. And using this graph to give me an idea of what the graph of that function is, right? What's the behavior of the function? And I found those 2 points. I just went ahead and mentioned those on this graph, those x-intercepts. Well, remember, that's where the function equals 0. So, I mean, if you take f prime and set it equal to 0, right, that's how you find x-intercepts on a graph. So that's all I did to get those, just so we could label those, nothing more than that. Where is that function equal to 0? That's your x-intercepts. Here's another example, f of x equals the square root of x plus 3. All right? Find f prime of x. So, you know, we've done examples earlier where we had some radicals. Because again, we keep saying as soon as once you plug in to the definition of the derivative, then it's all about evaluating the limit using whatever trick tool or process you have. So here's f prime of x. Our limit as h approaches 0 of f of x plus h, which would be x plus h plus 3 square root of, minus f of x all over h. And then now I'm back to evaluating this limit that has radicals, and this is one of the tricks that we used in the previous sections back in 2.2, where I'm multiplying by the conjugates, right, to remove the radicals. So multiplying the numerator and denominator by the conjugate, which is square root of x plus h plus 3 plus the square root of x plus 3. And then remember, when you're multiplying conjugates, the product, the sum and difference, the product is the difference of squares. So I square the first square root, and I've got x plus h plus 3, minus the square of the second square root. And again, there's those darn parentheses that I see left off all the time. Because of that subtraction, I do need to distribute the negative. So I've got x plus h plus 3 minus x minus 3, and then combining like terms knocks out the x, knocks out the 3. I'm left with just h. Now notice the denominator, what I did. I just rewrote that as h times all of that stuff. You don't want to multiply that out. You don't want to distribute, because remember, what's going to happen? We keep saying with these limits, every single time, what has to happen at some point is that has to go away. And so if I multiplied this out or distributed the h, I would then have to turn around and factor it so that that h could be divided out. So just leave it in factored form, because we know what the objective is here. We know what the outcome has to be. So Leave it in factored form instead of multiplying it and then having to turn around and refactor. So then once we simplify that numerator, we're left with h over all of this stuff. So then there again, I can divide out the h, which leaves me with 1 over the square root of x plus h plus 3 plus the square root of x plus 3. Limit as h approaches 0. And now I can go ahead and plug in the 0. Right? So plugging in 0, that'll simply make that h 0 right here. And like I said, as soon as you plug in the h value, now you can drop the limit statement. So I've got 1 over the square root of x plus 3 plus square root of x plus 3. Or 1 over 2 square roots of x plus 3. So a different type of function, I mean, the process doesn't change. We just have to, tweak it depending upon the type of function that we're working with, and that is then f prime of x. Now, I also wanted to mention domain here, because there's an issue, obviously, with square roots. We've talked about before domains of radicals and also fractions. There's domain issues. And then the observation that we made earlier about the comparison between the domain of f and the domain of f prime. We said the domain of the derivative could be the same as the domain of the original function, or it could be smaller. Okay? So notice in this case, if I look at the domain of f, and again, quick reminder, how do I find the domain of a radical? Domain of a square root. When you have the square root or a square root function, I said we always take the radical, the radicand, set it greater than or equal to 0, and solve. So I get x greater than or equal to -3. And that then is the domain of f. All right, so -3 to infinity, including -3, right, because it is greater than or equal to. Now notice for the derivative though, right, f prime, that square root of x plus 3 in this case ended up in the denominator. Well, what significance is that? Well, the denominator can't equal 0. So for this function, yeah, I still have the -3 to infinity, but I have to leave off the -3 because if you plug -3 in there, then you're going to get 0 in your denominator, right? So this is a prime example, simple example of a function where the domain of the derivative and the domain of the function are not exactly the same. And in this case, I also wanted to remind you about the radicals and the fractions domain issues with all of those. And look at the graphs of those two functions. Right? So here's f of x. If you were to graph the square root of x plus 3, you get this graph. And then look at the graph of f prime. And notice what happens as x approaches 3. Right? You're hitting one of those vertical asymptotes. There's a vertical asymptote right here. So as x approaches 3 from the right, the derivative is approaching infinity. Look at the graph of f. Right, if we approach 3 from the right, if you were to draw in tan lines to this curve, what's happening to the slope of those tan lines? As you approach 3, the tan lines are getting steeper and steeper and steeper. The slope is getting larger and larger and larger. At that point, they're approaching infinity. Okay? They're just getting steeper and steeper. Draw tan lines or hold your pencil along that curve and trace it out. And as you get closer to that point, your tan line becomes vertical, right? But again, there is no tan line at that point because there's a single point there. I'm going to mention something about that here in a second. Okay? So there's the comparison between those two. And then it also shows you the domain thing, because -3 is not in the domain of f prime, and on that graph of that function you actually have a vertical asymptote. Now, there are different notations that we use for the derivative. Some are more popular than others. Some people just have their preference as far as which one they like to use. The notation that we've been using so far, that f prime notation, so that is obviously very commonly used. You also see a lot of y prime. I mean, because remember, that's all f of x is, right? Y is f of x, they're the same. So whether you use f prime of x or y prime, those are very common, just depends on which one you care to use. Here's a different little notation, dy dx. Now what that ties us back to is the whole idea of what the derivative tells you. Remember, the derivative comes from the idea of finding the slope of the tan line, which was what, change in y over change in x when you use the slope formula. So this dy dx kind of ties us back to that idea that the derivative of a function is the slope of the curve. It's the slope of the tan line at that point. It's change in y over change in x, right? So it brings it back to its roots. That's, again, another very common notation. The df dx, I mean, that's the same as dy dx. Instead of y, we use f, right? I don't tend to use that one too much, or really at all. I do use this one on occasion, that we'll see. And the difference is, I mean, look, these are notations, yes, but they're also algebraically correct. In other words, when I say df dx, that does mean d times f over d times x. It's still a product. And so I can rewrite that numerator as d times f of x, and that's still df over dx. Okay, so I mean, all these they're not just notations for the sake of notations. They are also algebraically correct. And we'll talk more about that as we go forward and see some different things that come up. These last two with the big D's, I don't ever use those. That's just, again, another way of showing the derivative of our function f of x, or the derivative with respect to x of f of x. And let me get into that real quick, but again, I'm going to have to get into a lot more detail about that later. When you have this notation, right, I mean, f prime of x, that's telling me that I'm looking at the derivative of the function f with respect to its independent variable, which is x. So in other words, it's the derivative of f with respect to x. When you look at this guy, dy dx tells me that I'm looking at the change in y with respect to change in x. Again, that's going to become a bigger topic as we go forward and get into more complex and subject matter. But keep this in mind, because I'm going to say it 1,000 times. When you are differentiating a function, the question should always be, what is changing with respect to change in what? In other words, if I'm looking at the derivative of f of x, calling it f prime of x, then I'm looking at the change in our function f with respect to the change in x. That's where this dy dx type notation is very helpful. It very clearly states that I'm looking at the change in y with respect to change in x, because you can be working with multiple variables. There's not, it's not always just y equals some function of x. The broader application as you go forward, especially if you're heading into, like Calc 3 and beyond in higher levels of math, and you're working with multivariable calculus where there's not just one input variable, maybe there's multiple input variables. And so which one am I calculating the rate of change with respect to? All right, so we're going to dabble with a little bit of that later, and we have a lot more to talk about before we get to that point. But again, I want you to understand this notation. It's not just an arbitrary notation that somebody made up and said, hey, this looks nice, let's use this. It actually has meaning, okay? So again, we'll talk more about that going forward. So the d and the ddx, those are called differentiation operators. Right? So again, like I said, I don't ever use the capital D, but I do use the ddx. Right? So I have this ddx of f of x. What this is telling me is I'm looking at the change in this function with respect to the change in x. Right? So ddx, differentiation operators, of course, they indicate differentiation or the process of calculating a derivative. Right? Anytime we see those notations. And now, depending which notation you use, like I said, people just have different preferences. Some people prefer the f prime, some prefer the y prime, and so on. Sometimes it just depends on how you feel that day. Sometimes I use f prime, sometimes I use y prime. If I define my function as f of x, then I'll use f prime. If I define my function or my equation as y equals, then I'll use y prime. We may use dy dx in a situation where it's helpful to use that to better explain what's happening, especially if we have different variables in play. So those are the main three. And like I said, the other one I have circled, this one, that's useful if we're just finding or talking about, say, the derivative of a particular type of function. And I want to indicate exactly what that function is that I'm differentiating. Right? So again, it's just different notations. There's no right or wrong as far as which notation you use. It just may be dependent upon what the situation is or what the circumstances in which you're using it. Okay. Definition. A function f is differentiable at a if f prime of a exists. And again, that's a fancy definition of saying that when can I differentiate the function? Wherever the derivative exists. Whoop-de-doo. But then we follow that up. We say f is differentiable on an open interval, whether it's the interval from a to b, a to infinity, etc., all real numbers, if it is differentiable at every number in the interval. Right? So it's kind of like, remember we talked about continuity, right? We said that a function was continuous at a point. Remember we had those three requirements that we had to meet for continuity. But then we also said that the function was continuous on an interval if it was continuous at every number in the interval. That's similar to what we're saying here with differentiability. Right, so if f prime of a exists, then f is differentiable at that number a. If f is differentiable at every number in an interval, okay, then we're differentiable on that interval. Now there is one difference that I want to mention here, and this is going to become a sticky point for some of us later as we start to apply more of these concepts. If you remember when we talked about continuity, we talked about continuity over a closed interval to where you could be continuous at every number in the interval. You could also be continuous at the endpoint of the interval. Now that may be meant continuous from the right or continuous from the left, depending upon which endpoint you were talking about. But you could have continuity at the endpoint of an interval. Notice here we're talking strictly open intervals. And that when I say that a function is differentiable over an interval, I never address the endpoints of the interval. And I'll kind of clarify as far as why here in just a second. So continuity can occur at the endpoint of an interval. Differentiability, never at the endpoint of the interval. Those are always open intervals for differentiability. The next example, that just goes back to that one that we had mentioned earlier. I've already kind of addressed that with the f of x equals square root of x plus 3. The domain we said was -3 to infinity inclusive. But then we found the derivative, and we said the derivative, the function was only differentiable on the interval from -3 to infinity, but not inclusive of -3, because f prime of -3 did not exist, right? Because that square root ended up in the denominator. Right? So that's the same one we already addressed. This next little diagram or graphs, this kind of addresses what I was talking about above, as far as differentiability on an open interval, never at the endpoint, at least in terms of the first graph that I have there, number 1. So these are graphically examples or ways that our function cannot be differentiable at a number. With the first one, number 1, we have a point of discontinuity. And this is why we say when we talk about differentiability at an endpoint of an interval, we can't address that. Because if you notice, if a was the endpoint of my interval, the derivative as we approach a from the left, the slope of that curve is positive. The derivative as we approach a from the right is different. If you look at the slopes of the tan lines, those are negative. So the derivative coming in from one point side and the derivative coming in from the other side are two different values. And if all I do is close this off and say, okay, I'm not even interested in looking at this part of the graph. All I want to do is look at this left side. And I asked you, just with respect to this part of the graph, what is the derivative at a? Well, you don't even know what's happening on the other side of a to be able to tell me what the behavior of the function is. Right? Now, I can address continuity, right? We can say that we're not continuous at a from the left, because as x approaches a from the left, the limit does not exist, right? Because a is undefined, or the function is undefined at a. Okay, so you got to be careful with there's a difference. Differentiability, continuity, those are two different things. All right, so before I get more on that tangent. So number 1, we have a point of discontinuity. So what does that tell me? Well, if I'm going to be differentiable at a point, I have to be continuous there. Remember when we talked about continuity, I told you continuity was a big player. It plays a big role in a lot of these other concepts. Maybe not always in the forefront, but it's always at work in the background. And we have to be careful about whether or not we have continuity or not to make certain observations about the behaviors of our functions. So differentiability is one of them. So I can't have a point of discontinuity, so that means my function cannot be differentiable anywhere where it's not continuous. Right? Number two, though, notice I do have continuity at a, but there is no derivative there. We call that a corner. Another word we use there is we call it a cusp, if you want to use a fancier word. Okay? But it goes back to like I was talking about with number one. If you draw your tan lines as you approach a from the left, you look at the slope of the tan lines, they're all positive, and they're getting steeper and steeper. As we approach a from the right, those tan lines there are all negative. And again, they're getting steeper negative as you approach a. So you have the slope of the tan line approaching different values. And then right when you hit that point, remember the slope of the derivative is the slope of the tan line at a point. Well, which tan line are you talking about? Are you talking about this one? Are you talking about this one? I could even draw a tan line there, but it's not the direction of the curve. Okay. But the idea here is you have two different behaviors of your function on either side of that point, and there's no smooth transition from one side to the other. Okay. So bottom line, if you have any kind of sharp corner or cusp on the graph, you cannot differentiate the function there. The third possibility, these are not the easiest to see, and they don't really happen very often, at least for the functions that we work with, is if you have a vertical tangent. All right. So, like I said, you don't see a lot of these, but if you were to follow the tan lines there and you get to that point where x equals a, right at that point, the tan line does get vertical. And so if you remember back to, again, basic algebra, the slope of a vertical line is undefined. Right? Slope of a horizontal line is 0. Slope of a vertical line is undefined. So if your tan line is vertical, then your slope is undefined, which means you have no derivative. Right? The derivative is not defined. So those are graphically. So again, visually, three ways that you can tell if a function is not differentiable at a point. You either have a point of discontinuity, or you have some type of corner or cusp, or there's a vertical tangent. Right? Now, big theorem, the next one that's stated. Right? So this is one of the ones, like I said, we keep talking about continuity and differentiability. This is the one that gets misinterpreted all the time. Theorem that says if f is differentiable at a, then f is continuous at a. So that goes back to what we were saying. You can't have a point of discontinuity and be differentiable. So if f is differentiable at a number a, then it is also continuous at a. So differentiability means continuity. But the converse of that is false. So this is what we're saying with numbers 2 and 3. Notice 2 and 3 are both continuous at a, but they're not differentiable there. So differentiability guarantees continuity. Continuity does not guarantee differentiability. And we don't want to misinterpret that, and that's what ends up happening if you're not careful. So if I'm differentiable there, I'm continuous, because I can't differentiate at a point of discontinuity. But if I'm continuous, that does not mean that I'm differentiable. Maybe I am, maybe I'm not. So the next example is just to put some wording and notation and all to that. So state with reasons the numbers at which f of x is not differentiable. So there's a graph of a function. So again, I'm just saying that we're not differentiable at x equals -2 because of that point of discontinuity, right? Don't tell me something like there's a hole in the graph. Let's be a little more precise and specific with these descriptions. That function is not differentiable at -2 because it's discontinuous there. And then the second point of discontinuity is at x equals 2 because of that corner on the graph, right? So don't say like there's a point there, because there's a point all over the graph, right? Every point on there is a point. So be specific when you're describing these situations. If it's not differentiable, it's for one of three reasons. Either it's discontinuous, there's a corner, or there's a vertical tangent. Okay. Higher derivatives. Now this gets back to the fact that we said earlier, our function f, if it's differentiable, then its derivative f prime is also a function. And since f prime is a function, then it has its own derivative. We'll call that f double prime, or the second derivative of our function f, which is also a function, and then would have its own derivative. We'll call it f triple prime, or the third derivative, and that's the notation that we use. We use those little tick marks for f prime, f double prime, f triple prime, our first, second, and third derivatives. But again, what is the derivative? It's the rate of change of a function. So what is f prime? It's the rate of change of f. What is f double prime? It's the rate of change of f prime. What is our third derivative? It's the rate of change of our second derivative, right? Because individually, each of these are just functions. And each derivative describes the rate of change of the previous derivative. Now, once you get past the third derivative, because we just can't keep putting tick marks forever and ever, from the fourth derivative onwards, we use numbers. Not only do we use numbers, but also notice I put it in parentheses, so that would be the fourth derivative of f. If you don't put the parentheses, then it looks like you're taking that function and raising it to the fourth power. So we don't want misinterpretation there, so you have to be clear. So now, for our purposes, we are going to deal primarily with the first and second derivative. Now we'll touch the third derivative just to remind us that we could really do this infinitely. You know, you can differentiate it and differentiate and differentiate forever and ever. But once you pass the third derivative, the notation has to change. Right? So we put numbers there in parentheses to indicate the derivative. All right? But like I said, we're going to be pretty much restricted to the first and second for the purposes of things that we're going to be looking at. So here's f of x. Again, this is the one that we did earlier, so just to bring in a higher order derivative. If f of x is x cubed minus x, find f double prime, f triple prime. So we found f prime earlier. We went through the process and we found f prime. So here's f and here's f prime to be 3x squared minus 1. And yes, those of you that have done some derivatives before, you know how to use that power rule and find your derivatives and all that. If you're asked to use the limit definition, then I expect to see the limit definition. Like I said, I'll have a couple on your test that I'm going to ask you specifically to use the limit definition to find the derivative. And then we're going to get into all of our shorter processes. So again, we're just following the process. F double prime then, notice the notation. F double prime is the limit as h approaches 0 of f prime, right? F prime is the limit of f. F double prime is the limit of f prime. So f prime of x plus h minus f prime of x over h. And so again, we plug all that in. I've got the limit as h approaches 0. There's f prime of x plus h, 3 times x plus h squared minus 1, minus f prime of x. Remember I said earlier, make sure you're labeling everything clearly in terms of your different functions and derivatives, because when we're working with multiple derivatives, it's very easy to plug stuff into the wrong function. So keep everything neat, organized, and labeled. And then from there, it's all simplification. Right, so once you have everything plugged in, we're back to simplifying. Square the binomial, distribute the negative, etc., 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 combine like terms and all that good stuff, right? But that's all, again, just the basic algebra to simplify that numerator. And then notice again, at some point, I end up with terms in the numerator that all have an h. So we can factor that h out, divide out the h in the denominator, and I am left with 6x plus 3h. And then as h approaches 0, now we can go ahead and plug in 0 for h. So that would be 0, and I'm left with 6h. Now again, or 6x, excuse me. And that is our second derivative. That is f double prime. So then if we want f triple prime, well, we'll take the limit as h approaches 0 of f double prime, right? So it's all just a matter of keeping track of which function you're working with. So here's f double prime of x plus h minus f double prime of x over h. So f double prime, which we just found to be 6x. So there's f double prime of x plus h, 6x plus h, minus f double prime over h. And a little bit of distribution, combining of like terms. I'm left with 6h over h, which leaves me with just 6. Now remember, That's a limit, that's a constant, right? And I don't care what this is. We said very early on that the limit of a constant is the constant, right? So the limit as h approaches 0 of 6 is 6, and that is f triple prime. So we have our function, f of x, read through all that mess, x cubed minus x. We had f double prime, which was 3x, f prime, excuse me, which was 3x squared minus 1. F double prime, which was 6x. And now our third derivative, f triple prime, which is 6. Okay? But again, it's all relative in terms of notation. Right? Which function am I differentiating to get the next derivative? And then lastly, mentioning in this section back to some application, and we're going to talk more about this later when we get into the application part of this stuff. Right, we've already mentioned the position function and velocity function before. Well, again, we already know the velocity function. That's got to be the derivative of the position function because that's your rate of change. Right, that's where that came from. So we take our position function, f of t or s of t. We called it the position function. Remember, it said it's displacement. And units of the position function, are linear units, like feet or meters or inches or whatever our unit of measurement happens to be. Now our velocity function, we can go ahead and call the derivative of our position function because it's the rate of change in your position. So v of t is s prime of t, or f prime of t. That's our velocity function, and it carries units like feet per second, right? Meters per minute, miles per hour, that kind of thing, because velocity is change in position over time, right? Now, the derivative of the velocity function, which would then be the second derivative of your position function, is what we call acceleration. If your velocity changes, right, just think about yourself riding along in a vehicle. You're moving at some velocity because your position is changing over time. Well, when you speed up, right, you're accelerating. Your velocity changes. So that's acceleration. Units, rate of change in the velocity over time. This is, if you're not familiar with these types of units, it throws you off at first. Because remember, so what are we talking about? Velocity would be in feet per second, for example. And then if we're talking about acceleration, that's change in velocity over time. So that's where we end up then with something like feet per second, because that's our change in velocity, per second, which is our unit of time. So then I've got feet per second, or feet over second. Notice all this stuff works algebraically. So I'm dividing by seconds, which means I multiply by 1 over seconds. And I've got feet per second squared. That's algebraically how that works. I know those of you that took trig with me, we harp a lot on units and watching the units. Same thing here. I mean, the units work algebraically just like the calculations do. So, but ultimately, I mean, you just have to remember, if your position function is going to have units like feet, inches, meters, etc. Velocity is feet per second, meters per minute, miles per hour. Acceleration is always going to be feet per second squared. Miles per hour squared. Now you're squaring the time unit. It's not the whole fraction squared, it's just the time unit squared. Now those are the functions that we're primarily going to be interested in. I went ahead and mentioned the third derivative here just because we mentioned it previously. The third derivative of your position function, s triple prime, which is the derivative of the acceleration, which also makes it the second derivative of the velocity function. Right? It's all relative to which function you're talking about, but ultimately it is the third derivative of your position function. We call it j of t. It goes by a lot of different names. We call it the jolt function, or the jerk function, or the surge function, or the lurch function. Think about like the example I gave earlier where you're riding the vehicle, right? And so you've had a velocity and then you start speeding up, so you're accelerating, and then somebody punches the gas pedal again. Right, so you're accelerating and then you punch it again. What happens? You get kind of thrown back or jerked back into your chair. So think about that as your jolt function. Your acceleration changed at that point. But notice the units here. It would be feet per second cubed. It's always the change in the previous function with respect to time. So all you do each successive derivative is you just increase the exponent on the time unit, right? Because everything is changing with respect to time in this case. Now that's usual. It doesn't necessarily mean that time is always our bottom unit, right? But it is in most cases. We're talking about the position of an object and the velocity and acceleration of the object and so forth. But theoretically, that could be anything, right? Like I said earlier, what is changing with respect to change in what? So we're going to see some different things pop up, okay, when we get to the application stuff. That's section 2.8.